Hello and welcome to my class. I'm Grolin Annalisi from ThinkMO Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. What's a PP account is? +6 5834444290. Today's topic is STP, DHCP, CDP, and ACL. In the last class, we said something about part of STP. Let's do a review first. We said it before. In the network, if all devices use a single device, then the single line is connected to another device. You will find it creates a single point of failure problem, whether it is a line or a device. We cannot allow nodes in the network to have a single point of failure, especially the core nodes of the core equipment. So we often have to analyze the entire network topology. There are some redundant devices and lines present. Then once a redundant line or device is generated, may cause loop problems. So we need to be in the second layer network environment to run protocols like STP. Let it help us break the loop in the network. Please pay attention. We talked about TTL before. In fact, TTL is a means to prevent loops. But it can't break. STP can break the network loop. Run a protocol like this. There are no loops in the network. This is the basic role and characteristics of the STP protocol. So what kind of method does it use to break the loop? It is a vertical structure, starting from a tree root and spreading branches upwards. Then it walks up to a certain device. Is there not going to be a single line plugged back into the original first device? This is not going to happen. It is acyclic. The way it passes is block some ports in the entire network. Keep them logically blocked. Do not forward user traffic. Then it can lead to no way to generate this loop. Or in other words, it is eliminated after it is generated. And if something goes wrong in the future network, for example, maybe a line is broken, I can make another interface open automatically. Complete the normal forwarding. So the agreement itself is pretty good. Today, we will formally talk about the specific content of this agreement. We talked about BPDU in the last class. In the STP of our NA stage study, there are two types of BPDU messages. A configuration BPDU. What is written in the PPT now is to configure the BPDU. The message contains these parameters. There is another type of BPDU called TCN BPDU. Let's talk about configuring BPDU first. For the NA stage, STP actually involves little experimentation, because it learns its forwarding mechanism by default. So we are in the process of lecturing today. There will be more parameters to compare. So it might sound a little difficult to understand. Let's first talk about the parameters mentioned in the previous lesson. BPDU is called Bridge Protocol Data Unit. That is a message when all information in STP is interacting. This is the message form of their interaction. In the future, we are going to conduct some role elections. For example, I want to elect a root bridge, root port, specified port. You can see it here. They will compare the messages sent to each other. Let's look at this sentence. In the future, we will conduct role elections. Never mind what you choose. When we are doing role election, will depend on the path cost, peer bid, peer PID, local PID. Here are the parameters we compare today. These parameters are covered in this message. So after they send messages to each other, to determine the respective device and port status. That is, devices are updated through BPDU messages. This is part of what we talked about last class. In the last class, we first talked about RID. It's called the root ID. That is, root bridge ID. In this field, it is always filled with the ID of the root bridge. I will simply draw a picture here to explain. Let's take 3 devices as an example. This is 3 switches. They are sending messages to each other. The sent message looks like this. It's all here. Then in this message, this root ID is always the root bridge ID. For example, this is device A. This is device B. This is device C. Assume that device A is used as the root. Messages exchanged by all devices in the future. This is all A. Equivalent to. In order to ensure the stability of the topology as a whole, the root bridge will periodically send packets downward. Other devices will forward these messages. Then while they forward, we'll tell all devices that the current root is A. In order to ensure the stability of the topology. So this field is always filled with the root ID. There is a bridge ID behind. It is always filled here. The ID of the device that sent this message. I give a simple example. For example, now the first message is sent by device A. Then the field in the message it sends will be A. Then this field is also A. One means that device A now thinks that the root bridge in the entire environment is A. Another representative is that the device sending this message is A. When this packet arrives at device C, if there are devices below, if it wants to forward down, the root ID in device C is A. But here it will be changed to C. That is, it forwarded the message. Then it needs to change the bridge ID of the sending message to itself. Bid means that it will populate the device's own bid. Look down and there is a PID. It's simple. PID refers to a parameter in the interface, where the device is currently sending this message. The PID is calculated and generated by the priority of the interface plus the port number. So this PID is generated by the STP protocol. Don't worry about this. We're waiting while we do parameter comparisons. I will tell you about this PID again. Let's go back and talk about this root path cost. We didn't finish talking about this in the last class. Let's explain it next. For the current device, I will fill in the current distance of this device from the root bridge. That is, the distance between the device and the root switch. Then we're going to have a character election right now. First we will elect a root. A tree root selected by STP is actually a device. We call it root bridge, also called root switch. There is no distance between the root bridge and oneself in packets originating from the root bridge. Now overall this parameter is 0. There is no distance from this device to the root, because the root is itself. For example, now this is still a device like this. I'm connecting them now. It now sends out a message. Then the original RPC message is actually 0. When we calculate RPC, only the cost of the receiving port will be calculated. For example, the receiving port is now 1. Then when it receives the message, when it goes down, the RPC in this message will become 1. Then received by this interface, and then it sends down. We'll accumulate the RPC of this interface again. Further down, send out is 2. Then it is received by the next interface. This should have been mentioned when I talked about routing protocols before, such as calculating cost. We call the outgoing direction of the packet. If you send it here, it is this interface, or called the inbound direction of route convergence. Routing is reverse convergence like this. Then this is the incoming interface. Therefore, The message always has a direction, including that every time we calculate the cost, there is a direction along the way. This message passes through these interfaces. But for us, we will only count received ports. It is a cumulative value. For message 1, it receives from its own interface, received a 0. But it has to add its own. Then it is 1 away from the root bridge. Further down there are other equipment. It sends out 1. Its own interface is 1 plus 1. It is 2 away from the root bridge. Okay. You need to understand these parameters. Because wait, we're going to compare them. Then we officially start talking about some other election content. Before we compare these 4 parameters, I want to emphasize. If STP is to conduct roll election, our first step should be to choose the root. An environment Reagan must be the most important. Like a tree. The roots are the most important. So let's choose the root bridge first. That is, the order of our election is root first. After selecting the root, select the root port. After selecting the root port, select the designated port. Then the rest. Not a designated port. Also those ports that are not root ports will be blocked automatically. That is to say, I will not allow this interface to forward business traffic. Actually, the core concept of STP is to block ports. But STP does not just randomly pick a port and block it. It has to calculate first. After the calculation, the roll is determined. The last remaining ports are blocked. So this is a core idea of STP. What is the root? What is a designated port? Let's talk slowly. First we have to choose the root bridge. This is the first step. So how to choose a root bridge? I just said. All elections will be based on the packets sent by the device. Then the first step is when we conduct elections. Everyone must first know. The equipment on the second floor is actually incompatible with each other. For us, each switch only needs to start STP. It will consider itself the root. When you reach the NP stage, you will learn the specific packets of OSPF. Everyone knows that. Many agreements in the third layer are relatively modest. They don't think they have roles. But in STP they all think they are the root. It is now about to send a message to the outside world. Which parameter in the sent message will be filled with itself? Since it considers itself root, it will send out BPTU packets. Then this will fill it in. They start exchanging messages with each other. But the message exchanged between them is not called a loop. We will learn a lot of protocols in the future. In the protocol, various devices exchange messages with each other. They are not generated loops. The loop generally refers to the when a data is sent. This is a user's business data. It's a pretty standard ring. Now in this network, if passed like this is called a loop. However, the packets exchanged between devices are limited. Especially when the devices are all released at the beginning. The process is limited. And soon the interaction is over. This is not called a loop. They have to think of themselves as a bridge. Both fill themselves. The device thinks it is rooted. Will the devices all receive messages from each other? That is, prove that device A, device B, and device C can receive messages from other devices. They are interconnected 2 by 2. Then after receiving, they compare some parameters to determine who is the root. We will first compare the bridge ID of the root. So what does this parameter consist of? It must identify the ID number of the device inside. That is, it identifies its identity. So what is its composition? It is prioritized by 16 bits. Backplane MAC with 48-bit switch. Now many switches have no MAC address under the interface. In the early days, there were MACs under the switch interface. Each manufacturer is different. But now the second layer switch basically only has one backplane MAC. There is no MAC under the interface. That is to say, now this device has a MAC address. Then it will first use this MAC address, plus its current priority. Then to compare. This priority has a default value of. The default is 32768. Many parameters in the second layer default to this value. Everyone can understand. We can manually configure. I tell you this. If now there are 3 devices, the priority and the bridge ID of each device, all are by default. Then the MAC of the switch will start to compare. Among them, the smaller the MAC address, the better. So, first select the root bridge and compare the bridge ID. The smaller the parameter, the better. If we compare the priorities when we compare the results, we don't need to care about the MAC of the switch behind. So we are often in reality. The priority will be modified manually. That is, we can reduce some of the priorities. We do recommend that you manually specify the root bridge in the online network. Prevent misconnection and root grabbing. Because the root bridge is preemptible. You will learn some protection of BPTU in NP in the future. Then you will know the content. I give a simple example. Now there is a switch plugged in. If the priority of the device is all 32768. No modification. Originally it was the root. If it is connected now its priority. For example, it is 4096. Then it will take away the position of the original root bridge. It is no longer root. The location of the root bridge is taken away. Which means that the entire network topology will change. You should know. After the entire network topology is stable, BPDU packets will only be sent by the root bridge. Originally, the topology we maintain is that it is the root. Suddenly a device came in. It took the place of the root. Then the topology as a whole will change. Including what each device thinks is root has changed. It will have a considerable part of the time. It will bring some corresponding problems to the business. This is a matter of root priority. So we manually lower the priority of what you want it to be. The root bridge can be specified as 0. In the whole environment, we usually change to first set a 0 and set another 4096. You may find it strange. The priority must be configured as a multiple of 4096. So say the minimum value is 0. The second smallest value is 4096. When we configure a root bridge for it. Then configure a backup root bridge for it. The backup root bridge is when one day the root with priority 0 has a problem. Then the priority is 4096 to become the root. Generally speaking, suppose there are multiple devices in the environment. For example, this device performs best. I give it a configuration priority of 0. This device is the next best. I configure it to 4096. The two devices are 32768. By default, the first round of election compares the priority. We don't look at the MAC address. Compare priority. It sure is the best. Then it is the root. If it's gone, then it is the root. Not so performant, these devices will never be rooted. Certainly. If it's gone, then there's no way. We usually have to change equipment. It's enough for everyone to know this. Then we're done choosing the root bridge. There will only be one root bridge. Do you think there may be 2 root bridges? Some students may ask. Will these parameters not compare? It won't. Because we learned before. MAC address is globally unique. MAC address will not be repeated. So we must be able to compare. So there is no doubt that the parameters of the root bridge comparison are simple. Just these two parameters. A comparison will come out the result. In addition, we manually changed the switch backplane MAC to the same. Reboot next time. MAC address changed back again. It cannot be permanently modified. The MAC address is used as a hardware address and physical address of the device. It cannot be permanently modified. Everyone should know this. It is a physical address engraved in the chip of the network card. We also call it the hardware address. You can't configure fundamentally modifying the hardware of the device. This is the same as the bandwidth we changed before. A 10 megabit interface. A 100 M interface. You change it to gigabit. It's not a gigabit interface either. Physical parameters cannot be permanently modified. This is the first step. Let's move on to the second step. We are about to start the election of the root port. First note. The root port is to be selected on non-root devices. That is, there is no root port on the root bridge. All ports on the root bridge are designated ports. And you have to choose the root port on the non-root device. What port to choose as the root port? You need a measure. In all ports on non-rooted devices, we want to choose a port closest to the root. We also want to compare several parameters. There are 4 parameters to compare. The root port is actually the machine is connected to the nearest port of the root bridge. Only one root port on each switch. Except for the root bridge. Each device has one and only one root port. Let me draw a picture. I first draw 3 devices. I label them. This is device A. This is device B. This is device C. They are connected to each other. After the connection is complete, we're going to start the election now. Assuming the root has been chosen. Root is device A. We manually set its priority to 0. It is root now. No doubt. Between 2 other devices. Carry out some other port role elections. Now nothing more than. There is no root port on device A. Instead of having one and only one root port on the root device. That is. There is a root port between device B and device C. There are only 2 ports on device B. There are only 2 ports on device C. Both device B and device C need to receive data from their own 2 ports. Choose a port to be the root port. That is, these 2 ports in device B. One must be the root port. There must be a root port in device C. We will compare parameters. First let's compare the first parameter. It is called the root path cost in the inbound direction. This value is what we call RPC. Is the root path cost. We're going to compare. The smaller the comparison value, the better. When we compare, no matter what role is elected, all parameters are all smaller values are better. The comparison of almost all parameters in the second layer is that the smaller the better. In almost all 3 layers, the bigger the better. For us now, let's look at device B. Compared with device C, it is actually the same. Let me identify the interfaces of these devices. For example, this is the B1 interface on the left. This is the B2 interface on the right. Then the device C interface here. This is the C1 interface. This is the C2 interface. We are now going to select an interface in B1 and B2. Become a root port on device B. When we compare, in fact, it compares the cost of the root path in the inbound direction. The root will send messages to the outside world, which is then forwarded by the non-rooted device. That is, device A only needs to become the root bridge. All future BPDU messages will be sent by this device. Device B will receive such a message from the interface B1. The inbound direction refers to the inbound direction of the BPDU packet. If received from B2 interface, that's how the message came. What we are comparing now is the route path cost in the inbound direction. Then, for B1, its overhead is the overhead of this interface. For B2, its cost is B2 plus C2. That is, on device B, when comparing two interfaces, actually received by this B1 interface, assuming each counts as 1 first, we just calculate as an example. Because the default is the same. It is 1. 2 on the right. What we compare is the route path cost in the inbound direction. Then here comes a message. Only through one interface. Is 1. We calculated this when we calculated EIGRP before. The truth is the same. When packets come in, there are two interfaces. This is 2. If device B above, the RPC of the B1 interface is 1. B2 interface RPC is 2. We take a smaller value. Then this interface is good. The B1 interface is selected as the root port. But I want to ask, is it possible that I did the comparison and it didn't come out? Will there be such a situation? Okay. There is such a possibility. Some students may think, it seems like it should all be consistent by default. Let's draw a new picture. I now draw one more device. It is easier to compare, even if all its parameters are default. You will find it will also have some problems. I connect them. Now that's 4 devices. Let's say this is device A. This is device B. This is device C. This is device D. Suppose device A is still root. Device A needs to periodically send messages to the outside world. So where do we choose the port on this device now? We choose on this device. When device D makes a selection, which of the interfaces on the top and the left will become the root port? Let's take a look at a path it takes when forwarding. Device A now sends BPDU messages to the outside world from both interfaces. This message is sent to device B here. Send from device B to device D. Arrived at the interface of device D. Same. The packet sent by device A passes through device C. Also sent to device D. So now when device D is comparing the cost of the route path, how should the two interfaces be compared? It is now compared to this interface plus this interface. Assuming the default is 1. It is 2. Then received from the left interface. It is from the interface of device C plus the interface of device D. This is also 2. You will find, if we only compare the cost of the route path, it may not be comparable. That is, the route path cost received by device D from the two interfaces is 2. If this is the case, we will definitely not be able to compare. We will have a second parameter. The second parameter compares the bit of the upstream device. That is, forward bridge ID. The uplink device is the device that sends this message to you. For example, device B sends a message to device D. Device C sends a message to device D. Both device B and device C are called uplink devices of device D. If the RPC can't compare now, I will compare the bridge ID of the upstream device. In fact, the comparison is their priority plus MAC address. Is it possible that the bit of the upstream device is the same? Can you draw such a topology in your mind? In our picture, it is inconsistent. So if a picture like this In fact, it can be compared. But the reality is often not so easy. We have other possibilities. It's just that I can't compare RPC now. The bridge ID of the upstream device still cannot be compared. What's going on? I'll draw another picture to explain. For example, we only have two devices right now. I'll make a redundant circuit for it. I want to run two wires between two switches. The above is the root. This is 001. This is 002. So now let's compare. Suppose the following is device A. I choose the root port for device A. Let's first compare the root path cost in the inbound direction. The default is 1. Can't compare. Okay. Then compare the bridge ID of the upstream device. Now I found that the uplink device is only this one. If there is only one upstream device, then there is no way to compare. But we still have the port of the above device for comparison. Now although the upper equipment is the same, the device bid is the same as, but there are always differences on the device. For example, the two interfaces of the device are different. Then I just said, for PID itself is the priority of the interface. Of course it is also equal by default. But the port numbers are inconsistent. So I will now do a third comparison. The third comparison is the PID of the interface of the forwarding bridge of the peer device. That is, the PID of the interface of the uplink device. Let's call it the peer device. Because in this case, it must be that device on the opposite side. We'll do a comparison like this. Also, the smaller the better. So now in this picture, we definitely chose it. So now let's walk through the process. If so, the graph. We compare the first parameter and compare it. We choose it. If we compare it can't compare, we apply such a graph. We compare the second parameter. For example, if the value of device B is small, we choose B. This is the third picture. If this happens now, we choose it. Let me ask now. Is it possible that after comparing the interfaces of the opposite end, we still can't compare them? That is, I have now compared all three parameters. Inbound RPC, bid of the upstream device, PID of the peer device. But I still can't compare. Is there any possibility of this happening? Most people think it's impossible. Then I will draw a picture to explain. This is the root. There is a device like this in the middle of the root. I told you before. A hub is connected in the middle. Draw another device below. I connect them to each other. The above device is root. I now choose a root port for the device A below. We still compare parameters one by one. Every time we compare, have to start over. Make sure the first three are incomparable. First, the cost of the root path in the inbound direction is 1. Because the hub is not considered a device, so can't compare. Next, compare the bridge ID of the upstream device. Because the hub is a physical layer product, it's not a device at all. You can understand it as similar to a network cable. Its forwarding principle is very mechanical. No computing power. So it will not run any protocol. So actually the bridge ID of the uplink device now, or its bridge ID, can't compare. Then compare the PID of the peer interface. It's just an interface. The interface is incomparable. So what can be compared now? There is only one difference. If this can't be compared, then there's no way. Okay. The PID of the device's own interface is now the last parameter. Its two interface names cannot be the same. Priority is consistent by default. But the PID of the interface is inconsistent. So we will now compare. The PID interface priority is a 4-bit interface priority. 4 digits are 40101. The port number is a total of 12 characters. But this depends on each manufacturer. There will be some minor changes. Usually 1 this port, 2 this port. It is based on the port number. So 1 must be smaller than 2. So in this case it chooses 1. We now compare to this step. Is it possible that there is still no comparison? The future is when we troubleshoot every day. You will find that some may have been plugged in wrong. But we won't discuss these special cases when we study. Theoretically, as long as the topology we build is complete, as long as the wiring is connected correctly, then we must have a final result. So the election of the root port ends here. Compare these 4 parameters. If one of the parameters can be compared, stopped immediately. If you can't compare, we'll compare until the last parameter. In the end, I can definitely choose. The 4-bit priority also has a default value of, if I remember correctly, the default is 128. This will not be modified. Usually, we will not manually modify the priority of the port to make it the root port. This is the second step to elect the root port. According to the election root port, suppose we have now selected. You will find this is also what we choose in our courseware. If the parameters are not adjusted, definitely these 2 interfaces. It has an R written on it. R means this is a root port. It is this port closest to the root on each device. This interface is definitely closer to the root than it is. So these 2 are the root. Then after selecting the root, let's review. Here is a summary. When a non-root switch elects a root port, according to root path cost, peer bridge ID, peer PID, and local PID. These are the 4 parameters we just talked about. Okay. The root port is selected. Next we will start to elect the designated port. It also compares. The root port is called RP. The designated port also has its own name. It's called DP. For root bridge. All ports on the root bridge are designated ports. There is another sentence. There can be only one designated port on each collision domain. Remember what is called a collision domain? Look at this picture now. Device B and device C are in a collision domain. Each interface of the switch is a collision domain. Then the link between device B and device C. Actually under a collision domain. It is equivalent to the hub we just drew. The same is true for the hub. For the whole environment. This is a conflict domain. All hub interfaces are forwarding data. The overall scope of work of the hub is a conflict domain. I told you about the development history of the switch before. Hub. Bridge. Switch. A switch is a high-order bridge. I said that this is a big conflict domain in the hub. The best improvement made by the switch is an interface is a collision domain. So for us now, this is a conflict domain. But for hub networking, there's actually a big collision domain in the middle. That is, in this environment, we are connected through the hub. This is a conflict domain. So now under this collision domain, it has been selected as root. There can be only one designated port between them. By default, it must be a designated port, because it is a port above the root. Then in this picture, this port is naturally blocked, because the designated port under this conflict domain has been selected. So it gets blocked. But we generally don't talk about this special case. We generally speak according to the most regular, because we will see more such topologies in the future. so we follow it. We have now elected the two interfaces. These are the two root ports. These two ports are designated ports. We are now going to be on the link between device B and device C. Elect a designated port. Because each collision domain, there can only be one designated port. So there can only be one of them. So how do they compare?